Okay, so just a couple of reminders. So I guess homework, the first homework is technically due. The due date is tonight. It's 2 questions plus bonus. If it's not turned in tonight, Canvas automatically assigns a 0 to it, but there is this grace period that I have on homework assignments, generally about 4 days after. So what that basically means is if you don't turn it in tonight, it's no big deal. Canvas will give you a 0, but then if you submit it in the next 4 days while the availability of window's open, then that'll get submitted with no penalty. When it gets graded, that'll replace the 0. In fact, I think when you submit it, it probably gets rid of the 0. So basically, I think, follow the Canvas availability date, but if you can turn it in until I think September 10th at 11:59, and then on September 11th, that's when it will become unavailable and the solution set will become available. And then after that, I can't accept any late assignments. And so the goal is for you to turn it in tonight. That's why there's sort of the due date there. But if something happens and you need a little bit extra time on homework assignments, because there's no drop policy, I give you this longer grace period. So this like 4-day grace period. But then after that, it's kind of a hard deadline. So ideally get it in tonight. Several of you already have, but if you can't get in tonight, the next couple of days, you'll probably be fine. And that's kind of what I'm summarizing up here. The next lecture, Thursday, is over lecture C1, which is over another reading in the chapter. So there's an ICA for that, and there's Lab 3. Some of you already turned in Lab 3, so you may be a little bit ahead of this, but we're going to be introducing Monte Carlo methods. So if those of you who've taken reliability courses or things like that may have already seen some of these things, but for everybody else, to bring everybody up to speed, we'll be doing a couple of different Monte Carlo type exercises, and we'll actually see a little bit of that in class as well. So, but the Monte Carlo method you'll be implementing will pretty much be all Excel based. And so still no really sophisticated simulation software quite yet. You're still getting used to the methodologies. So that's kind of everything going forward. As I have mentioned before, there are these competitions which you can use for your final project submission. You should be able to get access to Arena in a number of different ways. See Canvas for instructions on that. If you don't like the IISC competition, but the deadline to enter is the end of September, there's also the FlexSim competition. FlexSim is a competitor to Arena. There's also Simio, which is another competitor to Arena. So the FlexSim one is specifically healthcare focused. If you learn Arena or Discrete Event System simulation in this course, it should be pretty easy to pick up FlexSim or Simio, even though we focus primarily on Arena in this course. So there's those options as well. So that's all, and I'll just have those announcements pretty much till the end of September. So that's pretty much all of the announcements and updates. Any questions? Questions online? Okay. All right, so the second part of the homework assignment is filling out a table like this one. We went through all of those steps last lecture. In case you missed that, if you go back, we kind of step through each one of those. And if you need more help on that, there is a video where I basically open up Word and I build a table like this, and then I go through an example. And then I also have a PDF out there of a bunch of solution sets to a homework exercise like this from past semesters and a few more. So there's a bunch of help out there. But of course, if you're still having trouble interpreting this table, then let me know and we can chat about that before the availability window closes. But basically, once you've got this, so you basically, the last time we showed, you start with this table up here, and you can then generate all of this table. And what all of this table effectively gives you is this timeline. And so it's a timeline of how arrivals, departures interleave in one of these single channel, single server queues. And so when we look at these timelines, we can see, well, here's all the arrivals. Those are pretty easy to figure out ahead of time because they're stacked one after the other. But the duration of each one of those arrivals, each one of those comes from the table up here. And because we know those durations ahead of time, we refer to them as activities. So they have durations that can be estimated or predicted without running the simulation. That's what makes them activities. So with in arrivals, again, because there's nothing delaying them, and we'll get to that term delay here, then you can pretty much figure out where all the arrivals are going to be ahead of time if you wanted to, just by stacking up, just by accumulating all of these inter-arrival durations, then you would get all of these times here. Now, the departures, that's a different thing. So the departures have to do with these service times. So customer 1 arrives, is served for 1 minute, departs. Customer 2's service doesn't start until 2 arrives, but then they're served for 8 minutes. Customer 3 arrives while customer 2 is being serviced. Customer 3 can't get into service. They have to wait till customer 2 stops being serviced. And so then they finally get serviced starting at time 12, and they get served for 1 minute, and so on. The times that actually involve the service can be predicted ahead of time. And so those are also referred to as activities. So activities have durations that can be estimated without running the sim, can be known ahead of time. But now that I look at the way these activities stack up, I see that there are gaps. And those gaps are the so-called delays. That gap I wouldn't have known if I hadn't run the simulation. The simulation allows me to figure out whether these inter-arrival durations, which come from one process, and these service durations, which come from another process, how they line up. And when they don't quite line up just right, then you get delays. And there's all sorts of delays here. So there's a delay here, which represents how much this looks like, this is how much the server is idle in this first one. So nobody is there. So the server is just sitting there waiting for someone. It's kind of wasted service. Here, this delay has to do with customer 3 arrived, but didn't get to actually start service until time 12. So customer 3 arrived at time 6, served at time 12. And so that delay represented that gap between kind of the arrival and when service could start. And we can keep doing that. And we gather all of these things up together, and we refer to them as delays because we don't know these durations until after we run the sim. We can't predict them without running the sim first. So delays are a key output of discrete event system simulation. We want to know, based on how we've organized our server, is this the best way to minimize all of these delays that have accumulated? That's kind of our goal. Is there a way we could reorganize things? Maybe it just means adding more servers. Maybe it means reorganizing the order of things so that idle servers maybe can do more than one thing, or idle servers maybe are introduced at a different part of the process. Those are the things we experiment with. And when we rerun the simulations with different organizational structures of our processes, then we study how does that affect the delays that come out. So that's the difference between activities and delays, inputs and outputs. An activity is an unconditional wait. It's predictable. It does not depend upon conditions of the system. Completion of that activity is what we call a primary event. That means it's scheduled. So in your simulation logic, if you know an activity is about to start, you always schedule the end of that activity. So that event happens because it was pre-scheduled. It was known ahead of time, regardless of what's going to happen in the system. This activity started now, so there will be an event in such amount of time that I can draw from some distribution that is independent of the sim. So that's what we refer to as a primary event. This is different than a conditional event, which would be triggered by some condition in the system. Like we could say that whenever the temperature of this oven reaches a particular temperature, then it triggers a change in the system. And so that would be a conditional event, and that event happens not because it was scheduled to happen, but because something changed in the system that crossed some threshold that generated that event and new logic to come out after that. So that's primary events, which are the most events in our systems are scheduled, and they're scheduled by durations, which we refer to as activities. This is different than our delays, which we also call conditional waits. So these are waits conditioned by the system. These depend upon the conditions of the system. And so they're caused by interactions of different activity processes together. So if we have a delay, it's because these processes are effectively misaligned. So you've got parallel concurrent processes that are operating, and because one lasts too long and the other one's, then the other one has to wait for it. So if there was a way to reorganize them, then maybe there wouldn't have to be as much waiting time. But it's that waiting time that comes from the misalignment of these processes that generates delays, and we measure those delays. So delays do not generate events, but events terminate delays. And so activities, if an activity starts, we're going to schedule an event at the end of the activity. But if a delay starts, it's something that we're measuring after the fact. So delays aren't generating an event, but the delay will be terminated by some other event that was scheduled, probably by an activity. So the waiting delay ends when the activity of service on another customer ends. So the end event from one customer is the start event of another customer's service, and thus the end of that customer's delay. So events kill delays, and activities generate events. All right, so we keep track of all these delays, as I'm hoping you're seeing now as you do these hand simulations, by placing entities onto internal lists, like the checkout line. So if a customer isn't available, or if a customer can't get into a server because the server isn't available, we put that customer into a checkout line, which is basically just keeps track of how many customers are in a queue. And then we can use that queue in our logic, so we can effectively generate conditional events later. And that conditional event might be at the end of one customer service. Then we can schedule, we can say, oh, it looks like a customer's ready. Let's move that customer into service. And then, so that moving the customer into service, that's a conditional event that happened. It happened right on top of the event of the previous customer ending their service. And then because that started an activity, we'd schedule a new primary event to when that customer finally finishes her service. So we manage that by keeping track of these lists like checkout lines. So any clarifications needed about this, the difference between activities and delays? Does that starting to make more sense? Activities are inputs, delays are outputs. Any questions online? Okay. All right, so this is just me kind of pointing out examples of this. If you think about the real world, hopefully this kind of resonates with you, is that delays emerge from concurrent processes with limited shared resources. If you had infinite resources, you'd never have delays, because processes could just get access to whatever resource they needed immediately when they needed it. But because we have limited resources, when a activity needs to start, if the resource needed for that activity to start is being used by another, then you generate a delay. So people have to wait to sit down. People have to wait to get out of for others to get out of the crosswalk. People have to wait for to be given a turn to go through the intersection. It might be that people have to wait for a car, for example, being manufactured, has to wait for the current set of parts to get installed on it before it can move on to get the next set of parts. So it's the fact that each one of these activities takes time, and there's only a limited amount of resources. There's only one robot that can put the doors on the car, and that process takes time. If there were an infinite number of robots that could put the doors on the car, you would never have to wait. So it's the limited resources and the concurrent processes that generate delays. Okay, so is that clear by now? Okay. All right, so as we covered last time and the time before that, generically, when you go into a problem like homework B1's question 2, you basically just walk through the future event list, the FEL, or the event calendar, which I call it up here, event calendar or future event list. And so you have to initialize the future event list, usually with an arrival event and maybe an end event. And then after that, you just walk through it. So you schedule new primary events based on the future end of new activities that are triggered at the logic now. So every arrival generates a new activity of waiting for a new arrival. That's why every arrival you process in the homework whenever you process an arrival, you know that regardless of what else happens when you process an arrival, you will schedule the next arrival. That always will happen. So there's always one arrival in the future event list in your homework. So the start of any new service is an activity unless it must schedule the end of the service. You can't start a server process in a DES without scheduling ahead when that process is going to end. Because if you don't schedule it, there's nothing else that's happening in the DES that will tell the computer when to stop it. So we have to then say, on average, how long does this service take? We're going to draw from a distribution that matches our stats for this particular service, and then we're going to schedule the end of it. And then we'll let the computer reach that end if it's the next event. And if it's not, it'll do whatever else is in the way. So then when you finally reach an end event, there are two types of end events. In the homework, it's a primary event, because I tell you, I think I said 13 seconds in the homework. So in that case, the beginning of the sim is an activity. The activity is do the sim, and we know ahead of time the sim is 13 minutes long. So we schedule the event of the end happening exactly at 13 minutes. Now it's totally arbitrary relative to the real system. We're just saying we're only going to simulate 13 minutes. Now we can also, in Arena or other systems, schedule conditional events as the ends. In other words, we can say, run until there are no customers left in this queue, for example. We may not know how long that will take. So, but we can have that conditional event that at the condition when all of the customers in this queue go to 0, that's when the simulation stops. And when you do that, that's an unpredictable duration, and you can actually use that as an output. So, so that unpredictable duration, that's kind of like a delay. So it's the idea is you could say, well, how long does this sim take to process all of the customers in the queue? If I change the sim, how long does that sim take to process all the customers in the queue? And maybe after my change, it's much faster to process all those customers. And so the duration of the sim itself could be a delay that we want to estimate, or it could be something that we schedule ahead of time, an activity, as you do in a homework. So we're only doing the primary events so far between Lab 2 and the homework, but we're going to see as we move on that there are ways to do conditional events where you can tell Arena, run this sim until a condition. Okay, so any questions about any of this? Sort of fundamental stuff for the homework. Questions online? Okay. All right. I'm gonna go through this very quickly because we already went through this step by step, but just on a single channel, single server queue, like the one in the homework, on an arrival, you see if the checkout line is empty. If it is empty, then that means you can put them directly into service. If it's not empty, it means they gotta wait. So if it is empty, you end up scheduling a new end activity for the end of service. If it is not empty, you add them to the checkout line and they have to wait. You always schedule a new arrival. So that's something you'll always do for every arrival event on the homework. For every departure event, then it's a similar sort of thing. You increase the number of departures, you increase the cumulative response time. On the homework, you also check to see, is this red bit here, this T, this current time minus arrival time, is that greater than I think 5 on the homework? And if it is, then you increment a counter. And if it's not, you leave that counter at F, what it is, or where it is. So then you remove the individual who left from the checkout line. You check to see if the checkout line's empty, because if it's not empty, you can now, that's a conditional event where you can now bring in a customer into service, and then from there schedule the activity of their service. And that's all that's going on here. And then if you've happened to hit that end event that's been scheduled ahead of time, then you just terminate the simulation. And normally that would mean maybe calculating some statistics as well. Like for example, this that S, if you divide S by ND, you'll get the average service time for all of the departing customers. So that would be something you would do at the end event, is to calculate all your summary statistics. And then that would end up generating, like we did last time, this timeline. And so I'm just sort of stepping through this tick by tick here, and we went through this every step of it last time, and we can end up generating this whole table which generates this whole timeline, and we go through step event by event. I'm not expecting you to generate the timeline in your homework, only the table. And notice I don't end with the end event, I end with the event just before the end event. So in this case, we ended at time 15, but I'm only showing you up to 13 because that was the last event, this departure event before the end event. So any questions about that? That's all the sort of stuff you need to complete question 2 of your homework. And we're going to talk about the bonus today. Questions online? I guess I should have put that up. Okay. All right, so if we were to say at the end, now we're at sort of the end of this chapter 3, if we were to say what are the concepts that we were going to review that we want to make sure coming out of chapter 3 you know, have some good definition of these things in your head, like what is a system, specifically a dynamical system, and a model. What's the system, the state of a system? What is an event in a discrete event system simulation? And what is a clock in a discrete event system simulation? Know what is an entity and how are attributes related to entities. Know how lists are used when we do these simulations. Know what, in sort of this, I haven't used this term very much, but this event record or this event notice. So be able to read, basically read the future event list. That's kind of really all that I'm saying here, is make sure you understand how the FEL, the event calendar, works and what are stored in the event calendar. And then finally, what's the difference between an activity and a delay? Those are sort of the fundamental concepts that we want to know coming out of this chapter as we move forward. So any questions on any of these topics before we move on to what we need to know for the bonus? Questions online? Leave those words up there. Okay. Great. Well, let me look at this for just a second here, and I think maybe haven't done an attendance exercise in the middle here for a little bit, so may as well do that. Just to keep things random. If I can get my mouse back. Hold on for a second. Okay, good. So the question I'll ask here is, what is another name for a conditional weight? So I said we have unconditional weights and conditional weights. So the question here is, what is another name for a conditional weight? In other words, a weight that is conditioned on the state of the system. W-A-I-T. Okay. All right, so the bonus on your homework is saying, all right, you've learned how to do this manually. What's one way we can do that can automatically calculate all this stuff for you? And can we do this with a spreadsheet? So not using a spreadsheet to hold the table, but to set up a bunch of formulas to have the spreadsheet do the entire execution for you. So you write 1 or 2 lines, you fill down, and it did the whole homework assignment for you. So how do we do that? And so when we think about discrete event system simulations and spreadsheets, we need to sort of think about fundamentally what is a spreadsheet. And so if we think about programming languages, they come roughly in 3 forms. So programming languages can be procedural, like C, Fortran, Pascal, BASIC, where you write procedures and subroutines, and those manipulate data structures within the program. And so the programs are a list of steps, and we use this term imperative, which means that, and these are not, I'm not going to quiz you over what a procedural language is or anything. I'm just trying to provide context here. And so we use the term imperative to describe these languages, and that means that the statements made in the languages change the state of the program. So these programs really do have an analog of a dynamical state like we see in discrete event system simulation models. Now, there's also object-oriented programs. And so in this case, this is sort of a modification of procedural where we don't focus on a list of steps, but we focus on objects that have things that can be done to them and ways that they can communicate with other objects. And so we generally don't have data out in the open. We put data hidden, encapsulated inside each of those objects. And so instead of interacting with the data directly, you interact with methods which themselves interact with the data internally. It's like, you can't know my heart rate, but you can ask me what my heart rate is. I can measure it and tell you. And so in this case, you still have this idea of a sequence of steps, but you're just kind of putting the procedures in sort of a different spot and the data in a different spot. Now, the third type, which is sort of the most fundamentally different, is so-called functional. And so examples of this are Lisp, Scheme, Haskell, ML. And so these functional languages, which is going to be the important thing here, is that a program output we view as a mathematical function of its input. It is so-called declarative. And so we don't emphasize a sequence of steps that modify state. Instead, we just specify relationships from inputs to outputs. And then we just get an output, and we have no idea sort of how, in the recipe sense, the output was calculated. We just know that the output has a certain relationship to other variables in the program. So there are no side effects that change the program's state. And so if we think about spreadsheets, spreadsheets are a declarative programming language. They are an example of this, where if you were to put a number in one cell and a formula in a bunch of other cells, you actually don't know what steps the program is using to calculate those formulas. All you know is that at every instant of time, you assume that the relationship you put here is correct relative to all of the other cells. And so the relationships are always true, and it's doing some sort of, you are programming the spreadsheet, but it's unclear how the numbers got updated. You just know that these relationships had to be the case. And that's why spreadsheets are also known as cell-oriented data flow programming, which is a type of declarative model. So it's a type of functional programming. So because it's a type of functional programming, there is no state in a spreadsheet until you get into like Visual Basic or something, and we're not going to do that. So the idea here is a plain vanilla spreadsheet with all its formulas interacting does not have the concept of state. So then that makes us ask the question, and how could we implement a discrete event system simulation in a spreadsheet? Because a discrete event system simulation is all built around the idea of state variables. And those state variables changing over time. So that's kind of what we want to build here. So in this example here from Banks chapter 2, this is on page 47, then it gives us inter-arrival times and service times, just like we did on the homework, part 2, the regulation part. And then the question is, how do we fill in the rest of this table? Well, if we think about it in terms of a model is an abstract representation of a system which captures the formal relationships among constituents. And so this relationship is kind of the key thing here, is that we're going to need to fill in the relationships across time. And so rather than thinking of updating states from one step to another, we have to say, what is always true about the state variables in the next time step relative to the current time step? And if we can capture those relationships, then if we sort of fill down, then we will get a discrete event system simulation, even though we didn't formally move from step to step to step, from time to time to time. So to put it another way, notice that this spreadsheet is organized by customer. It's not organized by time. So time has really been spread out. There's a clock here, a clock here, a clock here. So it's more like this has been organized, spread out across space. So each customer has different times associated with it. Customer 5 has an arrival time, a time their service begins, a time their service ends. So in our previous one where we had the rows were each time, then we'd say what is everything that happens at time 0, and then what is the next time, and what is the next time, what is the next time. Here instead we're going to say what's everything that happens to customer 1, and what's everything that happens to customer 2, and how does that relate to customer 1, and so on. And so we're representing the same data, but we're representing across space and not spread across time. So let's see how we do that. So the easiest one of these is probably arrival time. So we know that if we look at the arrival time column here, it is the case from customer to customer that, and I mentioned this before when we were talking about activities, that the next arrival time is always the previous arrival time plus the corresponding inter-arrival time. So I could write this in sort of Excel language, and I could say like this cell here that says 14, that's going to be equal to whatever this arrival time was, whatever that cell identity is, E4 or something like that, plus D5 or whatever this is, where that's the inter-arrival time. So I'm just adding the previous one plus the one next to it, and that's what I get to that. So I can take those and fill down, and I get all my arrival times. So that's the way you get your arrival time. So it gets a little more complicated when we start thinking about some of these other columns, like time service begins. We have to say, what is an invariant about time service begins? The service begin time, how does it relate to the immediately previous state variables that I have available, or the immediately previous variables that I have available? And if we think about it, we could say, well, for every customer, when does their service begin? It either begins when they arrive or when the previous customer's service ends. And it kind of depends on which one happened first. So that's all we set up here. So the time service begin is the maximum of when that customer arrived or the previous time service ends. So if I know the time that the service ends, if I happen to have this column available to me, then I can compare. I can say, oh, the previous customer's time, they ended before I arrived. That means I immediately get service. Or their service time ends after I arrive. So that means I have to wait. And that's all that this is calculating here. So I can put in a little Excel expression for this column, which basically references the cell in the row above and the cell adjacent. And it compares the two of them and says which one is highest. And then it replaces it with that. That's all. So that 5 corresponds to that 5 there. But any questions about that? Does that logic make sense for the begin time for service? Questions online about this? Question online. Oh, that's my question. Oh, here. Online it said, what do we mean by no macros on the slide? And so up here it said with no macros. So this means that I'm saying you implement this in the very spreadsheet functional language way where we're just using formulas within the spreadsheet. We're not using Visual Basic for applications or any other macro language where a macro would allow you to implement the idea of state on top of it, where a macro could write things out to the spreadsheet as if it was a giant matrix, and then the macro could look at the matrix and then update it. And that would allow you to add states to the spreadsheet. So we're only using the formulas inside the spreadsheet. We're not putting any macros into it. The other question we have here is, can we resubmit homework twice after tonight's deadline? Yes, as long as the availability window is open, you can submit the homework as many times as you want, and the latest version will be the one that's graded. So I'll mark that away. Okay. All right, so next thing we need to calculate then is the waiting time in the queue. Well, it is always the case that the wait time for every customer is the difference between when their service began and when they arrived. So in this case, it's either going to be 0 or this difference. So this only references things in the current row here, where you can say, well, it's just 18 minus 16, that gives us the 2. So the waiting time is just those two things. As long as I have these pieces of information, I can get that waiting time. So then time service ends. Well, if I think about it, well, what is the time service ends? Well, without worrying about how things are calculated, it's always going to be the relationship that will always be true is the time service ends will always be the time service begins plus the service time. Now, this seems a little circular because if I were to go back to the time service begins references time service ends. So I'm saying that time service ends depends upon time service begins, but begins depends upon ends. Now, the key here is that each time service begins depends upon the previous time service ends, whereas each time service ends depends on the current time service begins. And that's what makes that work. Now, note also that if you were to fill in this time service begins and didn't also have time service ends filled in, these numbers would not have filled in because they require this to be available. So a lot of times when people are doing the bonus, they'll say, I thought I was implementing this correctly, but I'm not getting the right numbers. And I have to remind them, you have to fill in all of the formulas in order for everything to settle out. And so it's true that on my example here, because I just hid these things, these numbers filled in. But if I just did if I had not filled in these and entered these formulas into Excel, it would probably give me zeros or blanks here because things weren't filled in over here. But the instant that I put in this formula, then the time service begins would all fill down and everything would complete. So you have to kind of wait until you get all of your formulas set before you can evaluate if your spreadsheet is correct. So the only other two columns I have to worry about is how long does the customer spend in the system? Well, for every customer, the time you spend in system is just the time they leave the system minus the time they arrive in the system. And then finally, this is a one that wasn't in the main table, but decided to calculate anyway, since that's what Moorcroft did in his example, is that the idle time of the server. Well, if you think about that, in every single row, the server is either not idle or so if you think about like when this customer arrived, how long was the server idle before the customer arrived? And it's either the server was immediately busy and like it immediately shifted to this customer, or if there's a gap between the time service begins for this customer and the previous time service ends, that gap represents time that the server was just sitting there without a customer, and that's the idle time. And that allows you to fill in all of these cells here. And so with that, it's possible for me to compare the table that I filled out last time with the table that the spreadsheet filled out. So before I do that, so we can see that they match, are there any questions about any of these formulas for filling this down in the spreadsheet, for doing the DES without using state in the spreadsheet? Questions online? Okay. So I mentioned that your bonus solutions should match the solutions you got in your table. So if you were to look at the table you hand simulated in your bonus, we can do a couple of spot checks to see if the same system was simulated. Because if you had the same inter-arrival times and the same service times, you should get the same outputs. That's one of the features of DES here. And so the idea here is that, well, we can look at like, well, customer 3 departed at time 13. That's what it says up here. I can just pick randomly. Customer 3, when did they depart? Time 13. Well, I go down here, customer 3, their service ended and they departed at time 13. So that matches. I can look at another one here. So customer 3 here, I can see they arrived at time 6. They departed at 13. So if I look at their response variables here, they were in the system for 8, right? So, or they were in the system, sorry, for, must have been here. So 6, 13, for 7. They're in the system for 7. And so if I look down here, they arrived at 6, they ended at 13, they spent 7 in the system. So that matches up. I can then say, well, it looks like at clock 13, there were 16 minutes of service accumulated for the 3 customers who departed. Well, in that case, I can go down and see, okay, 3 customers. How long did each one submit in the system? 1 plus 8 plus 7. Well, that's 16. So that's where I get that 16 up there. So everything matches. So I have to know how to read it because time is sort of linear here, but it's spread across space here, but everything matches. So any questions about that correspondence? It's a way to check your work. Now, of course, as we get into more complicated DESs, it's going to be, that's the reason we're going to go to a package like Arena and not do it by hand and not use Excel, because it's good. It would be a pain to do it by hand, and you'd surely get something wrong just by forgetting something, because the event logic gets real complex. And it would also be a pain to set up the spreadsheet here, and it'd be a difficulty in communicating to someone what your process flow was. And that's the reason why we go to more sophisticated packages like Arena. But for these simple ones, we can do them by hand and with a spreadsheet like this. Okay, so there's a lot of spreadsheet variability within and between replications. What I mean by that is we look across customers, we can see that these customers all have a very different experience, and this is just one replication of the simulation. If I wanted to generate another experimental replication, I would draw a different set of interarrival times and a different set of service times, but I'd leave all of the rest of the logic the same, and it would give me a different set of outputs. So I can get variability both within a replication and across replications. And so I need to make sense of experimental outputs, which vary within and across, and I need to figure out how many replications do I need to run in order to make a compelling argument about these systems. And that's fundamentally what we do in this class, is to answer that with statistics. And so if we were to think about it, this is the same questions we have to answer with any empirical system. If we have a system like a single mouse, if you were to run a mouse through a maze and watch how long it took them to get to different portions of the maze, there would be variability across or within the mouse, in the durations from one step to another. But then if I put another mouse in the maze, you get a totally different set of numbers. And so the empiricist studying the mouse in the maze needs to decide how many mice do I need to run, and also design the experiment to account for the fact that the mouse's performance at one part of the experiment may not totally match their performance in another part of the experiment. So I have to deal with all of this variability. And so this is identical to what we're going to have to deal with the variability in our systems. And so we're going to use the same tools. So that's kind of my sort of question here is, how does any empiricist make sense of experimental data, of varied experimental data? And that's, using stats. And so, I say, what does the Guinness Brewery Company have to do with it? And I'll sort of tell a story when we get to it about how the t-test came out of exporting biometry. So basically stats used to understand variability in biology to understanding variability in beer. And that was sort of the birth of industrial statistics, is from that, came from Guinness Brewery bringing modern small sample statistics. So the idea that we can't grow rows and rows and rows of corn, we really only want a batch of that we only really want to sample a small amount to see if this batch of beer is any good. So how do we make the most rigorous inferences from the smallest amount of data? And that's where we got the t-test, and then other tests that came after that. And we do the exact same things with our computational models. All right, so any questions about any of that? If not, I want to do a little post-lab, and then we'll be done. But that's, I do have a couple other things to say about the post-lab. Questions online? Okay. All right, so the lab that you did, Lab2, the Muffin Sim. So this was, of course, a simulation where you had muffins arriving to an oven, and you had to decide whether to put the muffins in immediately or wait for a large batch of muffins. And so, so that was sort of the fundamental problem there. And you didn't know how many muffins were going to arrive, but you knew that every minute there, or every day or whatever, a certain number of muffins could arrive. And that varied from day to day to day. So, so we have to make modeling decisions here. So what are the entities here? Well, we can make two choices, which are both totally reasonable. We can say we can use muffins themselves as the entities, and that makes it very easy to handle the limited oven capacity. So the oven only can support like 30 muffins. Then, well, that's fine. So each individual muffin comes in, and once the oven is filled to 30, no muffins can get added to the muffin, to the oven. And so, so we don't have to worry about any complexities of breaking batches of muffins up or anything like that. They're nicely quantized with the oven. The downside of this is you get lots of spontaneous arrival events. And so if you got 3 muffins that arrived at the same time, you'd have to model that as 3 arrivals, each with 1 muffin. And each one of those arrivals would have 0 inter-arrival time. So it's a lot of weird bookkeeping. And then you have to do it on the other end of it with departure events. So then you're going to have 3 departures or 5 departures all at the same time. And so it just seems like there's a lot of extraneous bookkeeping to deal with this. And so the alternative is to form these muffin batches. And so the idea here is we can say, instead of 1 muffin arriving, a batch of muffin arrives, and each batch has a number of muffins, which is effectively an attribute of the batch. So that gives us a single arrival event and a single departure event per batch. The downside of that is sometimes we need to break batches into multiple, because you might say that I want to put 2 muffins in the oven because the oven only has spots for 2 of them left, but I have a batch of 5. So you have to take a 1 batch and then take the 2 in the oven and create a new partial batch of 3. So you have to have 2 partial batches, 1 partial batch that goes in the oven, the other partial batch that stays behind. So when we're building these DES sims, we have the ability to use batches as entities, but once you use the batch as an entity, you may need to generate partial batches later and deal with that kind of, like, in the middle of your sim, sort of destroying an old entity and creating 2 new entities with these 2 different sizes. And that's totally possible to do. And you can actually do both in one simulation. You can have batches arrive, you can have them be turned into individual entities, run through the sim as individual entities, and then get batched at the end, or vice versa. So there's all sorts of ways we can do that. But I wanted to introduce the idea of batching in this muffin sim. All right, any questions about this idea of using batches as entities? So instead of every muffin being an individual entity, as you might think, because the stats might be on at the muffin level, we're actually using the batches, like groups of muffins, as entities, and then possibly having to break those groups up. Does that make sense? Hopefully it does. You've all done the lab at this point, or most of you have done the lab at this point. Okay, now, the thing about it is if we have batches arriving, we now have a random number of muffins in every batch. And so so we've got every day, we know consistently we're going to get a batch of muffins arriving, but we don't know how many muffins will be in that batch. And so we've randomized the number of muffins. We haven't randomized the arrival distribution. So the time in between arrivals is standardized, but the number of arrivals per arrival, the number of muffins per arrival, that's what's randomized. And this is actually very similar to things from the stock market. And so when there are examples of portfolio management models, so there are dynamic portfolio management models, which basically put money in and out of different equities, different stocks, and then measure how the prices go up and down in their simulated strategies. And in order for those to work, they need a simulated price signal. So they need a way to sort of say, what's a realistic way for prices to rise and fall across all of my equities to test out this. And so one of the things that and so this is actually very similar to the muffin example, where basically every day or every minute, depending on what you're simulating, you have an arrival of a price, and that price might be different than the price from the day before. So the stock might be, $5 a share now, and then the next day, the price might be $6 a share or $4 a share. And so you know that every day you're going to reevaluate the stock, but how much it changes every day, that's the random factor. And so, so they have to create models for these price changes, the same way you might create a model for how many muffins arrive each day. And so a lot of times they use things like these constraints where they can say each day's price is normally distributed, so it has some mean and variance, but we're going to make the relationship from day to day to day what's called a martingale process. And what that just means is that the average for tomorrow's price equals the actual price we use today. So it's kind of like every day is a normal distribution, but they're all anchored in mean to the previous day's actual price. And if you do that, you get a continuity of price where if your price is like $100 a share, the next day it's probably not going to be $2 a share. It'll be very rare. It'll probably be close to 100. So the distribution around the previous day's price is going to be normally distributed. But then if you zoom out, it allows the price over a long period of time to float very high and get very low. And so that if you use that constraint, then you can then fit the remaining parameters, i.e. the variance of that normal distribution, to actual price data. And with that, hopefully you've got sort of a fictitious but realistic price signal that you can test a bunch of your different portfolio management models to see how well some of them win and some of them lose. So that's an example where the modeling process of modeling the price changes is not really any different than the modeling challenge of modeling how many muffins arrive. So I got 3 muffins arrive yesterday. The next day, how many muffins arrive? Well, probably not 300, but maybe after several days, I'll get 300. So maybe there's small variance from the previous day, but then each one of those small variances will add up so that over long periods of time, there'll be large variances. And that's something that we could build in to this number of muffins that arrives. But we know there's going to be some muffins that arrive per day. So that's an example of how this muffin sim actually could relate to other stochastic simulation things we do. So what you guys did though is I gave you that arrival rate. I said this is how many muffins are arriving, and you either tested both a greedy policy. So that could have been anything from 0 to 9. So I had different muffin schedules from 0 to 9 based on that. So some the groups who got a 0 had one set of muffin arrivals, but they used that same set of muffin arrivals for both greedy and nearly full. The ones that had a 1 had a different set, and so on. So I'm not sure which one this one is, but let's call it the 0 set. So if you got a 0, and it may not be actually the 0, but if one of you out there, let's just pretend it's 0, did this, then what you should have found is that the greedy one had an average time in the system per muffin of, let's say, 3.92. But the nearly full policy produced an average time in the system of 4.18 or so. Now, when you look at that single simulation, it looks here like greedy is better because the muffins spend less time on average in the system. And if we only ran this one replication, that would be maybe, would seem like a totally reasonable thing to say. But we have to ask, does there statistical significance to this observation? And once we get that statistical significance, do we have practical significance? So let's see what I mean by that coming out of that. So this is actually all of your data from here. So there's 10 points here and 10 points here. So the circle point should match up to the same circle over here, but the scaling is different. So that circle and that circle correspond to that circle and that circle. But the asterisks, those are the other data sets. So if this was ASU ID is ending in 0, then this might be 1, this might be 2, 3, 4, and so on. So 10 data points here and 10 data points here. So now when I look at this, the question still seems pretty clear, but it's a little fuzzier. It still seems like across all 10 of the different muffin schedules that there's somehow these red points tend to be lower than these blue points. But there is overlap right here. And so that overlap suggests that still, these 3 points of overlap with these 2 points of overlap, it still might be that these points up here and these points down here just hit there by total fluke. It was random chance. And so this is what I mean by getting to statistical significance and statistical difference. Is there a difference between the greedy policy and the full policy? Can we say that with statistical rigor? And so at this point, I'm guessing there is, but I can't say that rigorously. So there is, a way that we can try to add some statistical rigor. Do you know of a test where if I were to say, what is the difference in average between the average greedy performance and the average nearly full performance? How can I say, well, here's 10 data points. Do these 10 data points come from a distribution whose average is less than the distribution that these 10 blue data points came from? Is there a test that allows us to do that? What is that test? The t-test, right. So I could do a so-called 2-sample t-test with these data. And that would be the test I would do, that if it came out with p less than 0.05, then I could say that these set of points likely came from a distribution whose true mean was greater than this set of points. But I can't use a 2-sample t-test because a 2-sample t-test assumes that these 10 points were totally independent of these 10 points. That's a requirement for a 2-sample t-test, is that the data points you take from one population were unrelated to the data points you took from the other population. But were these independent of each other? And if you think about it, each one of you used the same muffin schedule to generate one of these points and another point. So anybody with 0 in their ID use the same muffin schedule to generate this data point and this data point. So because these points are not independent of each other, like I could have given you, I could have said all of the greedies, all of the people with an ASU ID that ends in 0, I'm going to give you 2 muffin schedules, a greedy muffin schedule and a nearly full muffin schedule. And they will be independent muffin schedules. And so then I could have given each one of the digits. So those who end in 1, you get a different greedy and a different nearly full, and so on and so forth. But because I all gave you the same muffin schedule to use on both greedy and nearly full, then I can't use a 2-sample t-test because each data point here is paired with a data point over here. So what do I do? And so, by the way, this idea that I gave here, this is called common random numbers. And we're going to see this in lectures K and K2, or K1 and K2, where the idea here is I can generate 2 different models, say a baseline model, an as-is model, and an intervention. And I run the same customers, the same simulated customers through both. And then I say, for those same customers, which one was better, the as-is model or my intervention? And by doing that, I increase what's known as statistical power. I actually can run fewer simulations by doing that, as opposed to just running a totally independent set of customers for as-is, as I do for my intervention model. And that's part of what I was modeling here by giving you all coupling those 2 things together. So what I can do is I can plot instead, I can link each one of these things together. And so now you can see that 0 is linked up to 0 here. Let's call this 1 is linked out to 1 here. Basically, every line is coupling together the data point from the greedy schedule. So it's the same muffin schedule. So it's like this line here corresponds to 1 muffin schedule evaluated at nearly full and evaluated down here at greedy. So does everybody understand this plot that I have here? Like where the lines come from? There are 10 lines corresponding to the 10 digits, 0 through 9 of your ASU ID. And they're linking together the muffin performance for greedy and nearly full for each muffin schedule that was corresponded to each one of those 10 digits. Does that make sense? And this is a common graph that we'll see when we do paired analysis, when we pair up these things this way to increase our statistical power. Now, when I plot it this way, I hope you see there's a much clearer visual pattern. Whereas before, these two data points overlapped with these three, making me worry that maybe the pattern that I saw was just by chance. Here, every one of these lines has a positive slope. So in every muffin schedule, it was the case that nearly full was slower than greedy. So it is true that there are some muffin schedules where a greedy with one schedule is slower than nearly full with another schedule. But if I use the same schedule on both greedy and nearly full, on all 10 schedules that I gave you, it was the case that for every schedule, greedy was faster than nearly full. Does that make sense? The value of pairing things up. And so we're going to revisit these ideas as we move on, but you've done it, so I wanted to point these out where we got it. I can take, this is one way we often plot these data when we have these paired examples. The other thing I can do is I can take all of these differences. So if I look at like, take this blue minus this red, or this blue minus the paired red, and I can plot them this way, where I've got all the blues as open circles down here, and there are paired reds on top of it. So now the x-axis are the ASU IDs. So now I can see that the ASU IDs that ended in 0, this is the greedy data they got, this is the nearly full. The one that is in 1 got this. And notice again here, in this visualization, all the red dots, all the nearly fulls are for every single schedule always greater than the open circles, the greedy dots at the bottom here. So I can tell from here that even though there are some schedules for which nearly full seems to, like, if I were to compare this nearly full, or sorry, this greedy down here to this nearly full up here, then the red is above the blue. But if I were to compare, say, this greedy to this nearly full, for that different set of muffin schedules, it looks like this greedy is better, is worse than this nearly full. In other words, if I were to compare just across those schedules, it looks like maybe nearly full could be better. But if I make sure to run greedy nearly full on the same schedules, it's pretty darn clear that it's always the case that nearly full is slower than greedy. And that's the advantage of drawing it like this. Now, still, that's a visual. So does everybody understand this graph here and how it relates to your lab results? These are the real lab results. Questions online there. And this is a common way to plot paired data in these experiments. Okay, and so if I really want to make this rigorous, what I'm going to do is I'm going to take the length of each one of these dashed lines, and I'm going to plot it and compare it to 0. And that's what I've got here, is that I can take each one of these. So notice that back here, this one's pretty short, this one's pretty long. And so I'm basically going to take I think I do greedy, I think I say here, greedy minus nearly full. So if I take the blue dot minus the red dot, I'm going to get a negative number. Blue dot minus red dot will be a small negative number. Here, blue dot minus red dot will be a large negative number. I can take all those negative numbers and plot them, and they're all below 0. They're all negative. And now I can do a simple one sample t-test of these differences compared to 0. And that gives me a p far less than 0.05. And that is what we call a paired difference t-test. So in 380 or 385, I forget where we teach this, we often, we'll teach about the difference between a 2-sample t-test and a paired difference t-test. And we make it sound like there's something special about the paired t-test. A paired t-test is just a 1-sample t-test on differences. And so that's all I did here is I took the differences in each one of these pairings, and I compared the differences to 0 and did a 1-sample t-test. And that's what gave me this thing p less than 0.05. So here, I thought I could do a 2-sample t-test, but then I learned that the data weren't independent. So I had to pair them up and do a 1-sample t-test. And that is what allowed me to finally say that, yes, statistically rigorously, I can say for sure there is a statistically significant difference between greedy and nearly full, and greedy is better than nearly full. And we're going to learn about this as we go on through. We're going to try to learn which tests to choose and when to choose them as we get farther and farther into the semester. But I just wanted to point out this out as we go. So that's one thing. That's statistical significance. That's how we rigorously say that there is a difference. We use these tests like the t-test, like the ANOVA. But then the question is, there are a couple of questions. For one, which output should we use? And so I could use the average time in system, but I also could use the oven utilization, or I could use the queue length. And if I do pair difference t-tests on each one of these, even though the average time in system showed a difference, the oven utilization showed no difference between the two, and the maximum queue length showed no difference between the two. So, so the question is, which output do I pick? Do I just pick the one that shows a difference? If I do, then I could get into what's known as the fishing problem, where you might have seen these things where you say like jelly beans cause cancer, or not just jelly beans, but pink jelly beans cause cancer. If you went through every single color of jelly beans in a statistical study and then studied, somebody's risks of cancer, depending on whether they ate a red jelly bean or a blue jelly bean or whatever, if you do enough comparisons, you eventually, by chance, will end up finding one that at the 0.05 level will end up showing that there is a difference, that one thing might cause cancer. But because you did multiple comparisons, you're not allowed to use a 0.05 significance level. And that's something else that we're going to talk about here. It's the so-called multiple comparison problem. Is that when there are three outputs, you are not allowed to run a simple t-test on each one of these and then take the one that's different. You have to consider all three simultaneously, either by adjusting your alpha value, and this is what we'll talk about later in the semester, or running a special type of test like a so-called MANOVA, and that's something else that we'll talk about later. So in these sims, you're often going to have multiple outputs, and I'm just warning you now, you cannot simply take whatever output looks best and use it as your output. You have to consider every single output together before you do your stats and collect them together. The other thing that I want to point out here is that even though we detected a statistically significant difference in one of these quantities, it's not necessarily practically significant. So the average time in system per muffin, let's say, I don't know what units these are, but let's say they are minutes. Well, maybe our stakeholder says, you know what, 20% of a minute is not a significant effect. So yeah, you detected the difference between my two policies, greedy and nearly full, but the difference you found is effectively, gets lost in the noise. So that basically tells me I could, even though there statistically is a difference, practically there's not, and I should choose whichever one I want based on cost or something like that. So practical significance is very different than statistical significance. And so we really need an idea of effect size. And that's something else that we're going to talk about as we go into statistical power later in the semester. Now, it's a little more advanced, but as you move off into your jobs, the way you'll do this is you'll start quantifying effects using things like linear models, which again you totally see in like the A and the A5. So instead of having two oven thresholds, where greedy was 1 and nearly full was 20, because then we'll take the oven thresholds from 1 all the way to 30. And that runs in for every single threshold from 1 to 30, then measure each one of these things. Then at this point, I can actually fit a line, and that line slope tells me for every one oven threshold we had, what's the difference in time system provided. And that gives me a much better idea of not just is there an effect, but how much of an effect is there. So that's the reason why we try to shift from these either or models, like either an effect or not, to actually quantifying the relationship here. And the beauty of linear models is they also allow us to do fraction effects. And so the service time was for this model, I think it was like 3 minutes or something like that. If I were to increase it to 7 minutes, the relationship flips. And if I were to increase even farther to 14 minutes, it not only gets stronger, but it creates like this weird gap in between here. And so Well, you'll learn some more advanced stats courses is that you can use these multi-linear models with these multivariate statistics and actually start studying interactions where it's not the oven threshold, but it's the interaction between oven threshold and service time. And so certain service time regime, you'll want one oven threshold, and for other service time regimes, you'll want another. Basically, the small service time threshold, you might want to do the greedy strategy. But in the large service time, you might want to do the nearly full strategy. And so that interaction is super important when we talk about generalizing. So you might want to put the right term in your model. Well, it might be there will several to see if this relationship flips because it flips. What that means is that they use a higher service time in real life. Then your model is not going to generalize. Your model is showing exactly the long thing, which is why it's important for us to make our staff more and more sophisticated as we know, so that we can better understand the interactions between these variables. So that was kind of just an example that I'm primarily was to do and simulation model. But I wanted to at least show that simulation there's so much in that lab, from matching, thinking about common random numbers, to thinking about multiple comparisons, and so on and so forth. And you're going to see aspects of that throughout the rest of the semester. They're really important concepts. So keep that in mind for the rest of the semester. Not expecting you to totally have two tables paired down yet. We'll go over that. All right. So I think that's all I've got for you today. So let's start with final instruction. I'll get my mouse back here. Okay, here we go. So the last question for today is what is the maximum number of arrivals that you would that you will have in the future event in your homework? So in any line of your homework, you got a future event list, and the question is, what is the maximum number of arrivals in any one of those, not across all of them, in any one FEA, what's the maximum number? And that's all I got for you. We'll see you Thursday. Any questions online? If not, then I will end the call. It's been really good.